Hello everybody and welcome to our second hands-on tutorial in this artificial intelligence course. In this tutorial I'd like to show you how we can do k-nearest neighbor classification on a real data set using the scikit-learn machine learning library for Python. This library is one of the major libraries for machine learning and contains a lot of algorithms that we can't cover all in this course. So the website for the scikit-learn can be accessed here at scikit-learn.org, and this gives you an overview about all the methods that are included in the package. It provides a very good user guide, an API that gives you information about all the functions that are available, and a lot of examples. So we now go here to the user guide, and then you can see here that there are different subtopics. For example, a user guide for supervised learning, for unsupervised learning, model selection and evaluation, and so on. But there is also a very useful library, very useful topic, which is the seventh point here. It's dataset loading and utilities. If we click here, we can see here that there are different subtopics. So the general dataset API, toy datasets, real-world datasets, generated datasets, and loading and other datasets. So if we click here at toy datasets, you can see here a list of different functions from the scikit-learn package. And here is one dataset that we will use for this tutorial, the load breast cancer dataset. So if we click here, we get redirected to the function load breast cancer. And this load breast cancer loads and returns a dataset object, which is from a study about breast cancer prediction. So we can, for example, click here at the user guide to get more information, but we already get a first summary of what is included in the dataset. So there are 2 classes and there are 212 samples per class. So 212 for the class M and 357 for the class B. And then in total, there are then 569 samples with 30 dimensions. So let's click here at the user guide. Then we get more information about the dataset. So the dataset, if we scroll down here a little bit, we get here a small description about the dataset, which says that this is a copy of the UCI ML breast cancer Wisconsin diagnostic dataset. There is a link where the dataset was originally from. And here it says that the features in this dataset are computed from a digitized image of a fine needle aspirate of a breast cancer mass. They describe characteristics of the cell nuclei present in the image. And what we like to do here with this dataset, we like to predict, there are 2 classes, malignant and benign. We like to predict if the cancer for a specific patient or sample in this dataset is a malignant or a benign cancer. So what features do we get? The features are illustrated here, some attribute information. So it says there are 30 attributes, and here it's a radius, so the mean of distances from the center to points in the perimeter, the texture of the cancer, the perimeter, the area of the cancer, the smoothness, so for example local variations in radius lengths, the compactness of the cancer, concavity, concave points, symmetry, fractal dimensions. So these are different measures the authors have taken from the images, from the breast cancer images. And there we only can see 10 different features. So why it was written here 30? It's written 30 because the first 10 represent the mean of this feature. So the mean radius, the mean texture, the mean area. Then the next 10 represent the standard error. So the standard error of the radius. And the last 10 features represent the worst or the largest of these features. So that's the mean of the 3 worst or largest values for each of the features. So that's written here again. Of these features were computed for each image, resulting in 30 features. For instance, field 0 is the mean radius, field 10 is the radius standard error, and field 20 is the worst radius. And we will now use this dataset with this 569 samples to predict if a specific sample, if the breast cancer from the specific patient was malignant or it was benign. So how can we do this? Let's go to our Jupyter notebook. Let's create a new Jupyter notebook file, and then we can load the data set. And I already import all the other libraries I might need for this hands-on. So we like to generate some plots. So we write here matplotlib inline, that we can do inline inline plots. Then we import the PyLab, the plotting library. We import our NumPy library, and then we import from sklearn the datasets as datasets. So we like to extract the datasets, and I also load from sklearn neighbors import k neighbors classifier. So if we go back here, we can also go here to the user guide again, go to supervised learning, and then there are different models, and then we can, for example, go here to nearest neighbor methods, and there's the nearest neighbor classification. If we click here, we see that the k nearest neighbor classifier is implemented here, and here we can get more information about the k nearest neighbor classifier that we will use for this hands-on. But we come back to this later. So we first include or import all these libraries, so Shift Enter, and then we imported the libraries, and then the first thing what we do is we like to load the data set. So the data is the datasets, that's this object here, dot load breast cancer. Then we load the dataset, and now we have a new data object here. And this data object now contains a different information. And this information we can get again here by going to the documentation. So I'll just go back to my description of the Wisconsin data set here. And then, so when I execute this function load breast cancer, I get the following return values. I get a data object. So this returns data, and the data has the following sub objects. There is in data, there's a data object, and the data object has the shape 569,30. So this is our data matrix with all the samples times the features. It provides a target array. The target array are our labels. So for each of the samples in our data, we have 596 labels. So if it was classified to be benign or malignant. Then we have a feature names list. So what are the names of the features? So what are the names of the 30 dimensions? The target names list. So what do the targets here mean? And we also have a description of the data set and so on. So with this identifiers, we can access the data. So let's try this out. So if we now write here print shape of data column, and now I use the tabs that I make the printout a little bit more aligned. Then I write here str, and now I like to return the shape of our data in the data object. So our data, and then I can access with the dot the data object, data, and then I write dot shape. This should return the shape of our data. So how many samples does our data object has? Our X, and how many features. And then we do the same for our targets. And so shape of labels. And that's then the data.target.shape. If I execute this, the output looks the following. The shape of our data is 569,30. So it has 569 samples, 30 dimensions, and the target has the shape 569. So we see that the data looks the same as it is described here in the documentation. So we also can find out more about the names of the features, so what features are stored in our data and what are the label names. So that we do as follows. So we write the feature name. The feature names are the following: print data dot feature names. And then we also write here print the label names. What are the names of the names of our targets, and then we write print data label names, target names. Sorry. And if we execute this, we can see here our feature names are the following: the mean radius, the mean texture, the mean perimeter, and then after 10 features, it starts again the radius error, the texture error, so that's the standard error, and 10 features later, it's the worst radius, the worst texture. So the features here with the error and the worst radius are just other representations of our mean. And for this example, we only like to look at the first 10 features. So this we will do as next. And then we have here the label names. So the label names are malignant and benign. So this is how the targets are stored. So if we now look at, for example, data.target, then we get here a list of 569 values of zeros and ones. And 0 is malignant and 1 is benign. Then we know sample 1, that's the first position in target, has the classification malignant, and for example, the last sample here is benign. And we also can have a look at the data.data object. This is now a 569 times 30 matrix, so we have 569 dimensions, samples, and 30 features. So I said for this example we only would like to look at the mean features. We like to ignore the standard errors and the worst radius and so on, the worst values for this example. So what we have to do is we have to pre-filter our data and our data matrix. So we only like to access the first 10 features. How can we do this? So our capital X is equals to data. So we like to access our data objects. We like to get all the samples and only the first 10 features, so 0 to 10. That's a pre-filtering. So we now only only store in X the first 10 dimensions, but all the samples. So X should then have a different shape. And then we also say our Y is our data.target. There nothing changes. I just store it in the convention we used in the lecture. So capital X for the data matrix and lowercase letter y for the label vector. And then our feature names I have to filter as well, because we only like to keep the first 10 feature names. So we use also indexing again from 0 to 10. And we can try more or less now to check if everything worked as we wanted to have it. So we write here print the shape of X is the following, plus str x.shape. Then we do the same for our Y. The shape of Y is y.shape. Then we check if the shape of our feature names vector is the same. So there are only 10 samples should be stored. So shape of feature names plus str feature names dot shape, and then I execute this, and then we see, okay, the filtering work because the shape of our X of our data vector is now 569,10. So we have 569 samples and 10 features. We have 569 labels for all our samples here, and the feature names are also have a new shape. Only 10 feature names, the first 10 feature names for the first 10 features here are stored. And then we can also check how many malignant samples do we have and how many benign samples do we have. So we can use here Boolean indexing again. So we can write print the number. For this I use usually the hash, the number of malignant samples is the following. So I take my vector y equals 0. There I will get a truth value of true and false values, and then I can sum them up. So because we know false is stored as 0 internally and true is stored as 1. So if I sum this up, I know how many samples have the class 0, and then I can do the same benign samples, and there I have to use the class 1. If I execute this, you can see that it says malignant samples are 212 and benign samples are 357. We can check this if we go back here to the sklearn, and if we look here, it says samples per class 212 malignant, 357 benign, and that's exactly what we find out here. So this is what I usually do in the beginning when I load a dataset. I check are the dimensions as I would expect them. Is the information stored as it is written in the description or in the documentation of the dataset? And then I do also some basic checks to see how many classes, are the classes the same, and did the filtering work. So this is what I usually do in the beginning. And to get more information or to gain more insights into the dataset, I usually do some basic plotting of the data. I have to first familiarize myself with the data to more or less learn a little bit more about the data, to make myself familiar with the data. That's very important, because usually if we just apply blindly a machine learning algorithm on the data, we might fail because we haven't looked at the data, we don't understand the data. So we first have to visualize some properties of the data. And this we can do with PyLab or with Matplotlib. So let's write pl.figure. So we like to create a new figure. And I like to write now here fig size. So I change the size of my figure that we can see more. So it's 18,10. So it's the size of the figure. And then I like to create a box plot. So pl.boxplot. And here I have to provide the data I like to plot. So I'd like to provide box plots for my data matrix X. And then I like to also, so if I execute this, you can see here, there's a lot of output happening. And then you can see here a plot. The plot has now from 1 to 10. So there are 10 different plots that make sense. So every box plot here represents one feature. So that's the box plot for one feature. And what we also can see here, okay, we don't know what feature is what. So I would like to also show here the names of the feature that we can do by writing here, by extending this, by providing some X text. So pl.xtext. And we like to provide for the np.arrange for 1 to 11. That's, we start at 1 and we go up to 10. This we like to replace with our feature names. So we provide here the list of feature names, and we write that the rotation should be 90. So we like to rotate the name. And if we execute this, I get an error because I have a typo feature names. There's a S missing, and if I execute now, we see that we have now, instead of 1 to 10, we have here now the name of the feature. So the mean radius, the mean texture, the mean perimeter, mean area, and so on. Still, the plot doesn't look very nice. So we see here at the y-axis, the scale reaches from 0 up to 2500. So this box plot has a huge range, value range, which is here between, let's say, I think that's 100 up to 2500, and the other ones are very slow and we can't identify them. So what we could do is we could provide a log scale, and that we can do as follows. So first I would like to also provide a grid, so pl.grid, and then I like to change the y scale to a log representation. So y scale log, and if I execute this now, you can see that you have now a nice representation of your data. The y-axis is log scaled, and then you can see that many of the features here have a different scaling or a different value range than the other features here. And now you can get a nice representation about all the features. So you can see the mean radius of the tumor has this distribution, the mean area is this, and so on. So you get some feeling for the data and how the data looks like. So what's also very interesting sometimes is to not only get information about the distribution of the data in total, but maybe we would like to separate it by classes. And this we can do as well. So we can copy this here. Now we go to a new cell, and now I paste it here, and I like to now create one plot for the malignant class and one plot for the benign class. And this I can do with so-called subplots. So I can create here pl.subplot, and I have to provide here now how many subplots do I like to create. So how many rows do I like to have, how many columns do I like to have, and what image do I like to plot. So if I write here 1, the first number stands for the number of rows. I like to have 1 row, 2 columns, and I like to plot the first image. I write this here as a comment. So 1 row, 2 columns, first image or first plot. So I said I would like to create one subplot where I only show the malignant samples. So I have to filter X, and therefore I can use Boolean filtering. So I like to get all the samples where Y is equals to 0 and all the features. Then I provide a title for the plot, pl.title. These are my malignant samples. And this I copy as well, and this I also would like to do for my benign samples. So I create now in this range 1 row, 2 columns. I like to plot now the second image, and this one should be the benign samples. So I have to change the filtering here from y equals to 0 to y equals to 1, and these are then my benign samples. And this also would like to plot here in the log scale. So if I execute this now, then you see that I get now 2 plots, and they are in 1 row and there are 2 columns. So here you first get the first image, the malignant samples, which looks as follows, and here in this plot you get your benign samples. So these are the distributions for the different samples, more or less, for the different classes. And what's a little bit not so nice is that here for the y-axis you have different scales. So here we start at 10 to the power of minus 2. This is not displayed here, and there we go much larger than to the 10 of the almost to 10 of the 4, and here we start earlier. So we like to adjust this as well, and this we can do by providing different limits. So PL while we like to provide a new limit. So we like to start by 10 to the power of minus 3 to 10 to the power of 4. In the same axis, the same scaling I like to provide for my second plot. If I now plot this, we see they end at the same position, they start at the same position, and then we can compare the two different plots to see if there are differences between the features. And yes, we can see that there are some differences. There are some larger differences. For example, here, benign samples have a different mean area than here the malignant samples. And there are also some other ones. For example, here for the mean radius, here it's a little bit larger for the malignant samples than for the benign samples. And so you can see here subtle differences between the features in malignant samples and benign samples. That's already a first indication that there might be some separation possible between the different samples. So now we analyzed the data a little bit. We found out about the data, some interesting properties, and as the next step is that we try to learn a k-nearest neighbor classifier. And this we can do also with scikit-learn. So I create a new object that I call, for example, I create a new variable k-n for k-nearest neighbor classifier, and then I use the object or the class from the scikit-learn, which we imported before, so the k-nearest neighbor classifier, and then I have to provide some arguments. So first I have to provide how many neighbors do I like to consider. So n neighbors should be, for example, 1. I only like to have a look at the closest neighbor. I have to provide an algorithm, which we in our case use the brute, because brute force stands for the most simple implementation. We don't use any speed up, so we do it as we have learned it in our lecture. Then we have to provide a distance function or metric. So the metric is the Minkowski distance. And for the Minkowski distance, we can provide a parameter p, and we provide p is equals to 2. So what is if Minkowski is equals to 2? That's just the Euclidean distance. Where do I find out what parameters can I provide here? This we can find out in the documentation. If we go here again, and we go to the user guide, to the supervised learning, to the nearest neighbor methods. They have been under 6, so to the classifier, k-nearest neighbor classifier. And if we look here, we can see all the different parameters and the default values that we can provide. And here we can see the algorithm, which is, for example, the brute force. That's what we used. And here is p is the power parameter for the Minkowski metric, where when p is equal to 1, it's the Manhattan distance, and if p is equal to 2, it's the Euclidean distance, so the L2 norm. That is what we would like to use now. Then we can write k and n dot fit, and this means now I create a train my k and n algorithm, which I initialized here, and for the training I provide x, capital X, so our data and our labels. So that's the training step. And the training step, as we remember, just stores the data. And then after we train the model, we can do predictions. So predictions, our variable predictions is then k-n dot predict. We use our trained k-n model to do predictions, and we like to predict our samples x. So we just provide the data x. Then we execute this. We see that works. So let's see what is stored in predictions. In predictions, we now got here a vector of zeros and ones. That's then for every sample in our data matrix X, we get now a prediction. So the shape of prediction should be then 569. That's exactly what we get. So we get 569 predictions, one prediction for each sample in our data metric X. So how can we check now how good our predictions have been. What we could, for example, do is we could check, are the predictions the same as our labels y? So is this the same? And then we get, for example, if we do this logical expression here, we get an array of true and false values. So here we see a lot of truths. This we can, of course, sum up, for example, dot sum to see how many values are true. And then we get back 569. So that's very interesting now. Because does this mean that we did everything correct? Because we know from before we have the total number of samples 569. And 569 samples are predicted the same as y. Now we could ask a lot of interesting questions. So, first of all, is the number of neighbors equals to 1? Is k equals 1 good? What could be problems? Is it good to do predictions here on x? Why is it not good? Is this metric here which we compute, the number of predictions equals to the number of our true labels? Is this a good measure of how well our classifier performs? Or is this maybe a bad way of evaluating our classifier? These are all things you should think about for until our next lecture or our question hour. What do you think? Is it good or is it not good? Why could be, or why leads, when we set k to 1, why leads this to the a perfect classifier more or less? What could be the reason for this? That are very interesting questions. And this we will answer then in our next lecture. And we also could look now at, let's say, we copy this, copy it here, and we say now let's look at 10 neighbors. And then let's compute here this metric again. And if we execute this, we can see that we now predicted 511 samples correctly. So it's getting worse the more neighbors we select. In the lecture we said, if we select more neighbors, we should get more robust nodes. But here it looks like if I look at my closest neighbor, I get a perfect classifier. Does this make sense at all? That are interesting questions. Please think about them and then we will discuss them if this makes sense or not. This brings me to the end of this hands-on tutorial. Try to reproduce it. Try to think a little bit about it, and then we will discuss this in our next question hour. So thank you.